Hello, everyone. So last time we were looking at the case of system of ODEs, where we have a complex eigenvalues, distinct complex eigenvalues. Last time, so x prime equals ax, and let's say if a has, let's say two distinct, let's say a2 by 2, a has two distinct complex eigenvalues, let's say lambda 1 and lambda 1 bar. So we saw that if one eigenvalue is lambda 1, the other one should be the complex conjugate of it, lambda 1 bar. So by complex here, I mean non-real, because real numbers can be also considered as a complex number. But when I say complex, I mean it's not real. So there is some imaginary part. So that's what I'm assuming. And then we saw that in this case, find C1, let's say eigenvector corresponding to lambda 1, which is also a complex valued vector corresponding to lambda 1. Then construct, let's say C1 times e to power lambda 1 t, and write it in the form, let's say u of t plus I v of t. This vector here is complex valued, and this is a complex number. And overall, you will have a complex number here. You can write it as some real valued vector plus I times some another real valued vector. So here, u of t and v of t are real valued vectors or real vectors. Then we saw that the general solution can be written as, let's say some beta 1 u of t plus another constant, let's say beta 2 v of t. V of t and u of t and v of t. And v of t and v of t we already mentioned are real vectors, and beta 1, beta 2 are constants, real constants. So we can write the general solution in the real form. Everything is real here in this way. Now, what about the phase portrait? Phase portrait, in the case of complex eigenvalues, looks in one of the following forms. So it will either look like this, and like ellipses that the radius gets or the major and minor axis length get bigger and bigger. And so this is in the case of if lambda is equal to, let's say, I beta. If lambda 1, if one of the eigenvalues looks as can be written in the form I beta, meaning that the real part is 0. If the real part is 0, then you can write it this way. Now, then the phase portrait looks like this, and in the other case, spiral like this, with arrow getting farther and farther from origin, And this is if lambda 1 is equal to, let's say, alpha plus I beta, with alpha being a positive number this time. And to look like a spiral. And this time the arrow toward origin. And this happens if our eigenvalue can be written as alpha plus I beta, with alpha being negative this time. And this one, the arrow, the direction of arrow can be determined depending on the case and on the matrix that we have. So the arrow, the direction of arrow can be determined based on the matrix, the given matrix. So let's say in example above, let's look at the matrix that we had there in the example that we saw previous time. So what was the matrix? Matrix was prime equals AX, and A was 3, 9, minus 4, minus 3. And we saw that the eigenvalue, lambda 1, was 3 root 3i. So there is no real part. So that means we are in the case 1. So I can call this one case 1. And let me call this one case 2. And this one case 3. So we are in case 1 here because there is no real part for the eigenvalue. So we are in case 1. Case 1 above. Now let's see how we can determine the direction of the arrow. So let's say if the initial value, if we start with, let's say x of 0 equals 1 and 0. Let's say if we start from here. So to determine the arrow, to determine the direction of the arrow, let's say if x of 0 is equal to 1 and 0, then what would be the velocity at that moment? What would be the direction of the movement at that moment? If we start with this x of 0 equals 1 and 0, we know how to find the velocity. X prime is always equal to ax. So x prime here will be equal to 3, 9, 3, 9 minus 4 minus 3 times 1 and 0. So this will be 3 and minus 4. So 3 and minus 4 is a vector basically towards this direction. So the arrow looks like this. So that means that, you know, the basically our ellipse should be in a way that it has this will be the tangent line at 1 and 0. So how could this be the tangent line? So if I draw it the other way around, let's say if I draw it something like this. See, this one, what is the tangent line here? The tangent line looks like this at this moment, which can be the vector 3 and minus 4. So this will be the arrow, because the direction of the movement at this point is like this. So the arrow should be like this, so that the direction of the movement or velocity at 1 and 0 will look like this. So this is how we can determine the direction. So this not only gives us the direction or the arrow, it also told us like how the ellipse looks like. Is it going to look like this, for example, or is it going to look like this? So this one we could determine it based on just one information. We consider the initial vector to be 1 and 0, found the velocity at that moment, and the velocity is 3 and minus 4, that is direction of the movement. So I need to draw my phase portrait in a way that the movement or velocity at this point, 1 and 0, will become 3 and minus 4, which means a vector like this. So the ellipse should look like this, with this arrow, with this direction of the arrow, basically clockwise, right? Clockwise, so that the velocity at 1 and 0 will be the vector 3 and minus 4. So based on the velocity at t equals 0, which is 3 and minus 4, and it's a vector like this, we could determine the phase portrait and the direction of the arrow. See figure above. All right, so in this example, we found the solutions, the algebraic solution. We did the calculation, we found the solution, a formula for our solution, x1 of t, and also x2 of t, and then the general solution. And we also determined the phase portrait. This was in the case that the eigenvalue was purely complex. There is no real part. There is no real part, and we have only imaginary part in this case and in this example. All right, now let me give you an exercise. Find the general solution of x prime equals 3 minus 13, 5, 1 times x, and sketch the phase portrait. Part B, find the unique solution. Unique solution of the system above. If x of 0, let's say, is equal to 5 and 2. So how can you find the general solution? So let me give you a hint for part A and B. So hint for part A, we can find the eigenvalues first. So check that the eigenvalues will be 2 plus and minus 8i. So let's say lambda 1 is equal to 2 plus 8i. Remember, we only need one eigenvalue in this case, and we need the eigenvector corresponding to that eigenvalue. So let's say lambda 1 is equal to 2 plus 8i, and find the eigenvector corresponding to lambda 1, say C1, you can call it C1. Then you can construct C1 e to power lambda 1 t and write it in the form u of t plus ib of t. Then the general solution, as we mentioned earlier, can be written as, let's say, some beta 1 times u of t, beta 1 times u of t plus beta 2 times v of t. And then the phase portrait, we also need phase portrait in part A. We already mentioned that phase portrait would look like this, 2, because, we have this time the eigenvalue has a real part and the real part is positive. Remember, it's 2 plus 8i. So 2 it has a real part, which is 2, and 2 is positive. So phase portrait will be like the figure 2 above. And what about for part B? We want to find the unique solution, which means that we need to find these constants, because remember here beta 1 and beta 2 are some constants. And now how do we find the constants? If you have x of 0, if you have the initial condition, we can write x of 0 here, which will be beta 1 u of 0 plus beta 2 v of 0. And then that's equal to 5 and 2. So that will give you two equations with two unknowns, beta 1 and beta 2. And then you will be able to find beta 1 and beta 2. So for part B, x of 0 is equal to 5 and 2, which is beta 1 u of 0 plus beta 2 v of 0. And then this will give you two equations with two unknowns. And then you will find beta 1 and beta 2. Once you find beta 1 and beta 2, you can write the unique solution, find the unique solution. The unique solution will be beta 1 u of t plus beta 2 v of t. All right, guys, so please complete the calculation as an exercise. Now let's move on to the next case where we have a repeated eigenvalue. So far, we only considered the cases where we have distinct eigenvalues. Considered the case or the possibility where the matrix A has distinct eigenvalues, and the eigenvalues, if you remember, they were either real or complex. We provided a recipe in each case how to find the general solution. But now we want to consider the case where the matrix A has some repeated eigenvalues. So far, we only consider the case where all the eigenvalues were distinct. Let's say if A is n by n, we assume there were n distinct eigenvalues. And in the case of complex, we actually considered 2 by 2 only, but for the other one, we consider, for the real version, we considered n by n. Now let's consider the case where A has some repeated eigenvalue. So now suppose that A, let's start with 2 by 2 again for simplicity, has a repeated eigenvalue, let's say lambda and also lambda. So if A is 2 by 2, it will have two eigenvalues. So either they are distinct, which we already covered before, or they are repeated. So that means because it's only two of them, if it's repeated, you will have only one number which is occurred twice. So let's say lambda and lambda. So one solution, so now I can consider two possibilities. So case, two possibilities. Possibility one is that A has two linearly independent eigenvectors, let's say C1 and C2, corresponding to the eigenvalue lambda. This is possible because we already saw before that if you have an eigenvalue with multiplicity k, if let's say you have an eigenvalue which is repeated k times, then the matrix will have at most k linearly independent eigenvectors corresponding to that eigenvalue. Here we have an eigenvalue which is repeated twice, which means multiplicity 2. So A can have at most two linearly independent eigenvectors corresponding to that eigenvalue. At most two linearly independent eigenvectors, and of course at least one linearly independent eigenvectors. So that's why I'm saying there are two possibilities. If a number is at least one or and at most two, so it's either one or two. So either A has two linearly independent eigenvectors or has one linearly independent eigenvector corresponding to lambda. So A has two linearly independent eigenvectors C1 and C2 corresponding to lambda. Then the solutions, then C1 e to power lambda t and C2 e to power lambda t will be our two linearly independent solutions for the system x prime equals ax. And check that C1 e to power lambda t and C2 e to power lambda t are linearly independent. So we are assuming that there are two linearly independent eigenvectors C1 and C2 corresponding to lambda. Then we are saying that if you construct C1 times e to power lambda t and C2 times e to power lambda t, then you'll get two solutions for the system x prime equals ax, and these two solutions will be linearly independent. So my assumption is that C1 and C2 are linearly independent, and this implies that C1 e to power lambda t and C2 e to power lambda t are also linearly independent. We have seen a similar case before that where we proved that two or few solutions are linearly independent based on the linear independence of the vectors. You can simply use the definition of linear independence. Now, before moving on to the case 2, when do you think this situation happens. If A has two linearly independent eigenvectors and A is 2 by 2, what can we say about A? So note that this possibility, this occurs, this situation occurs. By this situation, I mean A having two linearly independent eigenvectors. Occurs if A is a diagonal matrix with diagonal elements lambda. So if A is 2 by 2, remember A here is 2 by 2. If A is 2 by 2, this matrix will have two linearly independent eigenvectors corresponding to the same eigenvalue if and only if A is a diagonal matrix with diagonal elements too. So this is in fact if and only if statement. It's valid both ways. So if it's diagonal matrix with diagonal elements lambda, then it will have two linearly independent eigenvectors, and also converse is also true. So I can say instead of if here, I can say if and only if, because it's valid both ways. Occurs if and only if the proof of this fact, proof of note. Let me prove one part and I can leave the other part as exercise. So if A, let's say, is a diagonal matrix with diagonal elements lambda, then A has two linearly independent eigenvectors, V1, let's say, equals 1 and 0, and V2 equals 0 and 1. So it's a very simple fact from Math 250 or linear algebra that 1 and 0 and 0 and 1 are linearly independent. These are elements of the standard basis for R2, and therefore they are linearly independent. And these two vectors are eigenvectors for A. Why? Why are they eigenvectors for A? Because A times V1. How can I check that some vector is eigenvector for some matrix? I need to calculate A times that vector. And then if I get a constant times the same vector, then that means that's an eigenvector. So A times V1 is equal to lambda 0, 0, lambda times V1, which is 1 and 0. And then I'll get lambda and 0, which is lambda times 1 and 0. So that means if V1 is an eigenvector for A with eigenvalue lambda, because A V1 turns out to be lambda V1. If A V1 is same as lambda V1, that means V1 is eigenvector with eigenvalue lambda. Similarly, A times V2 will be lambda 0, 0, lambda times 0 and 1. V2 is 0 and 1, which is 0 and lambda. And again, this can be written as lambda times 0 and 1, and that's lambda V2. So that means V1 and V2 are eigenvectors with eigenvalue lambda. And from linear algebra, we know that V1 and V2 are linearly independent. So in this case, the proof was simple, because if A is diagonal with diagonal elements lambda, we can introduce the eigenvectors that are linearly independent. We can say that just simply consider lambda 1 as 1 and 0, lambda 2 with 0 and 1, just the standard basis, elements of the standard basis. And these two are linearly independent, and these two are both eigenvectors with eigenvalue lambda. Now that's one way. Now what about the other direction? Because remember, I'm trying to prove an if and only if statement. So that means I have to prove two things. Other direction, if A has two linearly independent eigenvectors, let's say C1 and C2 with eigenvalue lambda. And remember, A is 2 by 2. I'm assuming A is 2 by 2. Then what does that mean? That means AC1 is equal to lambda C1 and AC2 is equal to lambda C2. Now, C1 and C2 are two vectors which are linearly independent. Now, we know that in dimension n, if we have n vectors which are linearly independent, then they automatically construct a basis for Rn. So here I have two vectors in R2 which are linearly independent, so they automatically construct a basis for R2. So recall that if, let's say, C1 to Cn are linearly independent, this is a fact from linear algebra. If you have n vectors which are linearly independent, linearly independent vectors in Rn, then C1 to Cn will be a basis for Rn. Here I have two vectors in R2 which are linearly independent, therefore they must be a basis for R2. So here C1 and C2, two linearly independent vectors in R2. So that means C1 and C2, the basis for R2. So if this is a basis for R2, what does that mean? That means if I consider any element in R2 like X, then X can be written as a linear combination of C1 and C2. So now consider an arbitrary vector, let's say arbitrary X in R2. Now C1 and C2 is a basis, so I can write X as a linear combination of C1 and C2. So therefore I can say X is equal to, let's say, some alpha 1 C1 plus alpha 2 C2 for some constants alpha 1 and alpha 2. So then what can I say about AX? So AX will be A times alpha 1 C1 plus alpha 2 C2. And I can write this one as, because alpha 1 alpha 2 are constants, I can write this one as alpha 1 times AC1 plus alpha 2 times AC2. AC1, we know it's alpha, AC1 is lambda C1, AC2 is lambda C2. So I can write this one as alpha 1 lambda C1 plus alpha 2 lambda C2. Alpha 1, alpha 2, and also lambda, they're all constants. So I can take lambda out, and then I'll be left with alpha 1 C1 plus alpha 2 C2. Alpha 1 C1 plus alpha 2 C2 is X. Remember, X is alpha 1 C1 plus alpha 2 C2. So this is lambda X. So what did we show? We showed that AX equals lambda X, which is same as lambda I times X. Because lambda I, if I is the identity matrix, 2 by 2 again, but whenever I is the identity matrix, I times X will be same as X. That's the role of identity matrix. That if you multiply it with a vector, you get the same vector back. So identity matrix times X will always give you X. Lambda times identity matrix times X will be same as lambda times identity matrix times X. Identity matrix times X is X. So this is lambda X. So this vector here, lambda X, on one hand can be written as AX. We just showed it above. On the other hand, can be written as lambda I times X, where I is the identity matrix. Because I times X is X, lambda times that will be lambda X. So this lambda X can be written as AX, can be also written as lambda I times X. And this is valid, this holds for every vector X in R2. So see, here I have two matrices. One is A, one is lambda I. The action of these two matrices on every vector X will be same. So that means these two matrices must be same. So this is also a fact from linear algebra, that if you have two matrices, that their action on every vector is the same. So that means those two matrices must be same. So that means A is equal to lambda I, which is equal to lambda times 1, 0, 0, 1. And this is same as lambda 0, 0, lambda. So here we use the fact that from linear algebra, that if AX is equal to BX, let's say A and B n by n matrices, and let's say X n by 1 matrix, for every X in Rn, then A and B as two matrices must be equal. One way to see this is to think about matrices as functions, like AX. You saw in linear algebra that defines a linear transformation. It's a type of function. Similarly, BX. So if you have two functions whose actions are on every input are the same with each other, so that means those functions must be the same, as long as the domains are also the same. So that's one way to see this. There are other ways to see this as well. But in any case, if you have two matrices, their action on every X are the same. That means those matrices must be the same, which is the case here. Therefore, we could conclude that A is same as lambda I. So we proved both directions. And the summary is, so if your matrix is diagonal with diagonal entries lambda, we have repeated eigenvalue this way by having a matrix, diagonal matrix with diagonal elements lambda, then A will have two linearly independent eigenvectors, and then the solutions can be written as C1 e to the power lambda t and C2 e to the power lambda t. And this situation happens only in the case where you have a diagonal matrix with diagonal elements lambda. So as long as we are in 2 by 2 case, so all things that I said are valid for 2 by 2 cases. We only consider 2 by 2 cases for now. In higher dimensions, let's say if you have 3 by 3, and let's say you have a repeated eigenvalue with, let's say, multiplicity 2 and 2 linearly independent eigenvectors, you cannot conclude that A must be diagonal in that case. So, but these things that I said are valid for 2 by 2 case. So now this is one possibility. Now the other possibility, I can give an exercise before moving on to the next possibility. So exercise, find the general solution of, let's say, x prime equals 5005 times x, and sketch the phase portrait. Now let's move on to the next possibility. So possibility number 2, if A has a repeated, let's say 2 by 2 again, has a repeated eigenvalue, let's say lambda and lambda, with 1 linearly independent eigenvector let's say C1 corresponding to lambda. Then we know one solution will be C1 e to power lambda t, right? So then C1 e to power lambda t will be one solution. Now, what about the other solution? Remember, because we are in 2 by 2 case, we are searching for two linearly independent solutions for our system. We know that we have one eigenvector, one linearly independent eigenvector corresponding to lambda, but what about solutions? We need 2 linearly independent solutions for our system. We know that this is one of them because we already have C1, we already have lambda, and this is a solution. Now we need to find another solution which is linearly independent with this one. So what about the other solution? So based on what we have seen before, that in the case of repeated, well, in this case it's eigenvalue, but previously we talked about repeated roots. We saw that we can multiply with t. We can consider the first solution and then multiply it with t. So in this case, it's C1 e to the power lambda t is one solution. Now, what happens if I multiply it with t? Do I get a new solution? So based on similar situations, we had before, we can consider the other solution as C1 times t times e to the power lambda t. Or we can at least try this. We still have to verify whether this is a solution or no. So if you say we can try, because previously we saw that if you have a repeated root, let's say 5 is a repeated root, 5, so e to power 5t is one solution, then t times e to power 5t could be the other solution. So let's see whether this works. Does this work? So let's say if I set x of t to be c1 t e to power lambda t, then can I say that x prime is equal to ax? Because if this works, if this is a solution, then x prime must be same as ax. So let's find x prime. What will be x prime in this case? X prime, for finding x prime, I need to use the product rule. So x prime, let's use product rule. Then I will have derivative of this function. So derivative of t is 1. So I can write it as c1 e to power lambda t plus, and then e to power lambda t derivative is lambda e to power lambda t. So I can write it as c1 t lambda e to power lambda t. So this is x prime, which is supposed to be equal to ax. Now what is ax? So ax will be a times, this is my x here, this is my x, a times this, c1 t e to power lambda t. Now I can write this one as a c1 t e to power lambda t. A c1, we know it's lambda c1 because c1, remember, it's c1 is the eigenvector corresponding to the eigenvalue lambda. So a c1 is same as lambda c1. So I can simplify this as lambda times t times e to power lambda t. And lambda c1 times a c1 is lambda c1. So lambda c1 t e to power lambda t. So I was hoping that this expression becomes equal to this expression. Well, this part of this expression is same as this expression, but then the first expression has this additional part. Therefore, overall, this expression is not same as this expression because these two expressions would have been equal if this expression was 0. But this expression is not 0 because C1 is an eigenvector, which is non-zero. Eigenvectors are always non-zero, and exponential functions are also always non-zero. This part is non-zero. So this expression overall cannot be equal to this expression because this part is non-zero and these two parts are the same. So let me call this expression, I can call it star. And let me call this one 2 star. So now star cannot be equal to 2 star since C1 e to power lambda t is non-zero. Note that C1 is non-zero. C1 is non-zero because it is an eigenvector. It is an eigenvector. and e to power lambda t is non-zero because exponentials are always non-zero. So that means overall the guess that we had did not work because it turned out that it is not a solution, so it didn't work. So that means we have to try another guess. So since the guess above didn't work, let's try. So what about if I try, let's say C1 t e to power lambda t plus another vector, let's say d times e to power lambda t for some vector d, which is to be determined later. So what happens if I add this term? Let's say this is the term that I considered before and it didn't work okay. But then what about if I add this term? Then overall, maybe I will have a solution. So let's see that. So in this case, see my x of t is C1 t e to power lambda t plus d e to power lambda t. So x prime will be how much? X prime of t will be, again, for the first term, I can use the product rule, C1 e to power lambda t plus C1 lambda e to power lambda t times t plus for the other term is d lambda e to power lambda t. So now x prime is equal to ax. I'm hoping that I can choose x in a way that becomes a solution for this system. So I'm hoping that my choice of x prime satisfies x prime equals ax so that it becomes a solution. And I know that x prime is this, so I can substitute C1 e to power lambda t plus d lambda e to power lambda t plus C1 lambda t e to power lambda t is equal to, must be equal to a times x. X is C1 t e to power lambda t plus d e to power lambda t. And if I simplify this, I know that a C1 is equal to lambda C1. We use this for the previous case as well. Remember, again, C1 is an eigenvector with eigenvalue lambda. So a C1 is same as lambda C1. So then I can simplify the right-hand side as lambda C1 t e to power lambda t plus a d e to power lambda t. If I expand the right-hand side, it's a times this, which can be written this, and a times d e to power lambda t, a times d, I cannot simplify it, I can leave it as ad. So this is simplification of the right-hand side, and this is supposed to be equal to the left-hand side, which is the addition of these three terms. Now, if I compare the left-hand side addition of these three terms with the right-hand side addition of these two terms, I can see that there is one common term which can be canceled out from right-hand side and left-hand side here. So I can cancel out this term with this term. And then I'll be left with the vector, if we say in order to the equation above to hold, the vector d must satisfy Must satisfy which equation? It must satisfy C1 e to power lambda t plus d lambda e to power lambda t equals the right-hand side, the term that is left, because there were two terms, one of them was canceled out, and I'll be left with the second term, which is AD e to power lambda t. I can cancel e to power lambda t from left-hand side and right-hand side, and I'll have C1 plus d times lambda equals AD. If I take this one to the other side, then the equation above holds if C1 is equal to AD minus lambda d, which can be also written as A minus lambda I times d. So what can we say? So we can say that x of t equals c t e to power lambda t plus d e to power lambda t becomes a solution for x prime equals ax if this vector d is chosen in a way that c1 is equal to a minus lambda I times d. If you choose d in a way that a minus lambda I times d equals c1, remember you have a, you have lambda, you have c1, you want to find d. If you choose d in a way that a minus lambda I times d becomes c1, then this becomes a solution for our system x prime equals ax. So it becomes the solution for x prime equals ax if we choose d such that a minus lambda I times d is equal to c1. So this is c1. So remember, we already had one solution, C1 e to power lambda t. We were looking for the second solution, which is linearly independent with the first solution. And our claim is that this will be the second solution. The solution of this form, you already have C1, you already have lambda, you want to find D, you can find D. D is going to be a solution of this equation, a vector that satisfies this equation.